Alright, welcome back to day 2 everyone. This is happy number. So in this question, we are given an input 19 and we want to split up its digits and then square them. So 1 squared plus 9 squared, 82. And then what we want to see is if we continue doing this, if we end up hitting the number 1. So if we hit number 1, it'll just loop endlessly at 1 because 1 squared equals 1. Or if it's unhappy, it's going to loop endlessly in a cycle that doesn't include 1. So in both cases, there's a cycle. One of them, the cycle is 1, and the other one doesn't have 1. Okay, so to do this, I'm going to show you how we can split up integer into its digits. And then the second thing that we'll do is how to detect a cycle. And then here we can go over briefly if we use a hash set versus something like Floyd's cycle detection algorithm. All right, let's get started. So first, we need to figure out how to split up this integer to its digits. So for us, it's pretty easy. We see that there's a 1 and 9, so we're done. But how do we tell a computer, 19 consists of, the first digit is 1 and the second digit is 9. So to do that, we're going to use an operator called the modulo. So the modulo, if you haven't seen it before, it returns the remainder of a division. So for example, if we had something like 19, what happens if we modulo it by 10? So what we can see is we have 10, and then we have 19, and then it fits into it once. We get 9 left. So here, this is going to be our modulo. Now the cool thing that we can do to extract the digit is you can see that right here, this is already the first digit. So the pattern we're going to use is we're going to have our number, and then we're going to modulo it by 10, and then we're going to modulo it by 10, and then we're also going to divide it by 10. And let's see what happens when we do this. So let's choose a bigger number. Let's say 681. Modulo by 10 is going to give us that 1 in the last because we have 680 divisible by 10. And then when we divide by 10, we get 68.1. Now we're storing it into an integer. So that means that all these decimals, they get truncated. We can't store them. So they just becomes 68. Now if we feed this into our next run, we have 68 here. Modulo by 10, we have 60, so the remainder is 8. And then when we divide again by 10, we're going to get 6.8. And again, this gets truncated. So we actually just get left with 6. And then we repeat again, we have 6. And then here, we can't fit any 10, so 6 by itself is the remainder. And then when we divide by 10, we get 0.6. And again, truncate, so we get 0. Then when we hit 0 here, we've noticed that by this time, we've actually extracted every digit. We've extracted 1, 8, and 6 in the reverse order, but it is the digits of this number. So let's go ahead and code this up. We will create a new function. Let's call it next. And we have some sort of output. And while n does not equal to 0, what we'll do is we have our digit is equal to whatever n is, modulo by 10. And then our sum is going to increase by the square of that digit. And then finally, our digit, we just divide it by 10 to get the next. And here we can return our sum. So if we want to check that this works, we can do something really quickly. Let's say 15 I++. Let's just print like the first 15. So let's do this and see what we get. All right, so 19 is the happy case. Oh, missing a return statement. Right. So let's return something dummy here for now. Return false. Cool. Run our code. Time limit exceeded. Where else did I go wrong? Oh, sorry about that. This should be n. We divide, so we feed in n by divided by 10. So that is divided by n. Okay, nice. So this is what we saw above. And then we can see once we hit 1, we kind of keep looping into 1. And let's see another example, a not happy number. So I run it on 62. And now we see that with 62, we see a loop. So let's see, 145 is the same. It's around here. So we have from 16 to 4. And then we cycle again back to 16, 37, 58. Okay, so now our goal becomes how do we detect this cycle? And then when we detect it, all we have to do is when we're in that cycle, is it equal to 1? If it is, then it's a happy number. If it's not, if it's any of these other 13, 42, then it's not a happy number. So there's two ways that we can do this. There's more than two ways, but the two ways that I want to talk about. One is we could use a hash set. So with a hash set, what we do is we keep track of every number that we've seen so far. So we've seen 62, 40, 16, blah, blah, blah. And then when we get down here to 16, we would see that, hey, we've seen 16 before, so therefore there must be a cycle, and then we'd exit. Now, the problem with a hash set is that we need to keep track of all the numbers that we've seen leading up to the start of the cycle. So an alternative algorithm we could use is we could borrow the ideas of Floyd's cycle detection algorithm. So with Floyd, let's see here. With Floyd, what we have is a turtle and a hare or a rabbit. And so what happens is that on every step, the turtle only moves by 1, while the hare moves by 2. And then what's going to happen is the hare moves by 2, the turtle moves by 1, the hare moves by 2, we check. Turtle moves by 1, hare moves by 2, we check. Turtle moves by 1, and hare moves by 2, we check. Turtle moves by 1, and lastly, hare moves by 2, we check. There is a point where the hare basically catches up to the turtle because it's looping around. And then we can see if this number is equal to 1 or not. In the happy case, when we hit 1, it's just going to keep looping around 1. So they'll catch up pretty fast. So we'll do a quick proof at the end of this video showing that the hare will always catch up to the turtle within one loop. But for now, let's assume that this works and we'll code it up. Okay, so what we want to do here is we want to introduce a turtle and a hare. The hare can take the next one. And while this turtle is not equal to the hare, we're going to move the turtle next. And the hare will move twice. And then what we return here is whether or not our turtle is equal to 1. Not a question mark. Okay, so that should give us what we want. And we'll try running it. This should be false. Okay, and let's try submitting it. And it's accepted. So it works. But when I first heard about Floyd cycle detection, I remember in the back of my mind, I was like, okay, but is there ever a case where the hare just happens to skip over the turtle every time, and they just in this loop endlessly just always skips over and they never meet up? So we can actually prove that this case doesn't happen. So the way we'll do that is let's give some labels. Let's say this is x0, x1, and blah, blah, blah. We have 2, 3, 4, 5. So here, x6, x7. So you can see with when you're going through, we have this relationship that x at a is equal to x at a plus however many loops that we've gone across times the length of the loop. So in this case, the length of the loop is 6. So that's how we get x0 is equal to x6, x1, x7. This will be 2 times 6 is 12, plus 1 is 13. So we have this relationship. And what we want to prove is, when we get into, when the turtle starts the loop, the hare has already gone around multiple times, maybe, and it's like somewhere here at some offset. And we will call this offset here y. So y is the offset of the hare. So in this case, in this example, we have 1, 2, 3. So y is equal to 3. That's the offset. So we want to say, well, when the turtle starts in the loop, so let's say mu is the start of the loop. After it takes, I turns, I steps, does it equal to the hare, which also began into the loop and has circled around for a couple of times now, plus it's at some random offset here, and the hare, every time it moves twice. So here we do plus 2i. Do these two equations, can we get these two to reconcile somehow? So in this case, a is equal to u plus I. So what we really want to know is u plus I plus KL is equal to mu plus K2L plus Y plus 2I. We want to see if this happens. So let's cancel out some variables. I here, there's a 2 here. We end up getting KL is equal to K2L plus Y plus I. We clean this up a bit. Let's get rid of that. Let's see, we have that L K minus K2 minus Y is equal to I. So let's dig into this equation a little bit. So we have Y, which is fixed. It's whatever the offset of Y is when the turtle finally starts the beginning of the cycle. K2 is also fixed. It's how many times the hare has circled around before the turtle finally arrived. L is also fixed. It's the length of the loop, but we can control K, which is from this equation, like which one do we want them to equal? So we can set K to be equal to K2 plus 1, meaning that we want to meet them within one loop. So if we do that, we get the equation, I'll write it up here, L minus Y equals I. So let's try it out here. So in this case, we have L is 6 minus 3 equals 3. What this tells us is that within 3 moves of the turtle, they're going to end up at the same node. So let's see this play out. So the turtle will move once, twice, we check, nothing. And then 1, 2, check, nothing. And this is a third one, check, they're at the same node. So it guarantees us that in I steps, they will meet. Now what we notice about this equation is that y is always going to be, a number between 0 and L because it's the offset between the start of the loop. So that means this I will also be a number between 0 and L. So we've proven that when the turtle hits the start of the loop, and the hare is wherever this hare is, whatever offset y is, within I steps, these two will definitely meet up again. So that's why the Floyd cycle detection works. Okay, that's the end of the video, and I'll see you guys on day 3.